Hi, I'm Sam Bentson at Aprovecho Research Center. I want to tell you about a project we've been working on for the past 2 years. It's a continuation of the test kitchen project we started 4 years ago, but now we're focusing on source ventilation interventions. So we have a natural draft hood and a forced draft hood and a fan above the stove. So let's go through what those things look like and the results that we got. To evaluate these different interventions, we had a test kitchen. This is an old drawing from the publication that we did 2 years ago. And it shows the outside dimensions of the room and the height, and it had a ridge here, so the height was taller in the center than it was on the sides. The total volume was 30 meter cubed.
I'm standing outside the test kitchen. There's a door inside me we jump up into to get into the experiment. We've got 48 holes on the bottom. That's how air gets into the test kitchen, the ventilation air. Then we have 48 fans along the top. They're wired to a big power supply so we can change the voltage and change their speed. That's how we set the air exchange rate in the test kitchen. Sitting here at the captain's seat now outside the test kitchen. We've got a set of holes in the walls here so you can stick your hands through and feed the fire. These are the continuously fed wood stoves we're always dealing with. We also have a window here so that you can open it up and put the pot on the stove or take it out. There's a computer where we watch the emissions in real time via the partial capture sampler.
This is a drawing of one of the interventions that we tested. It was a 12-watt fan. That's how much power it drew, and it was 16 inches. It wasn't from the floor, this diagram. It was measured from the subfloor. So it was about a foot from the floor is where the bottom of that fan was. So this is mounted on this outside wall that's behind the page, and so the smoke from the fire went up and got sucked out of the room. That was one of the interventions. That was the small fan. The next intervention was the same concept, but it was a much larger fan. So we basically had one row of these computer fans, and we had two more, and we had a larger fan, same position, and it drew the smoke out of the room. The next intervention we did was that same fan. So this is the outside dimension of the fan, and this is the wall where the smoke got blown out of. And the stove was inside this box. So this was a simple type of forced draft hood. So the stove was here, and the smoke went up, and it hit this square box, and then it got pulled out by the fan. And the last intervention we did was a natural draft hood.
Now I'm sitting in front of the natural draft hood. This is the final configuration that we tested. The stove goes inside, and we have some metal here to protect the wood, but all the heat is inside the stove. The hood itself doesn't take any heat. Then the exhaust gases come up and they hit these shoulders, and they go through the square chimney and out through the roof. When we were testing the natural draft hood, we had to change the experiment. All the forced draft experiments, they relied on the perimeter fans to establish the ventilation rate. When we first tested the natural draft hoods, those perimeter fans, the draft went through the fans instead of up the hood. The heat from the fire wasn't strong enough to create the pressure differential that was needed to draw the gases through the hood. So for the natural draft hood, we had to turn off those perimeter fans. The next thing we had to change with the natural draft hood was we can no longer rely on just these small holes to allow the air to enter the kitchen. Again, the draft wasn't strong enough, and we had to have a larger opening so that the gases could flow through the hole.
Here we have the average concentration of PM2.5 that we measured on the 1.6 meter plane in the test kitchen. For the uniform room ventilation, which was accomplished using the fans surrounding the perimeter, 48 fans on the top, set to 8.4 volts. That was almost 3,000 micrograms per meter cubed. That was the average over the test period, which was half an hour. Then when we had the 12-watt fan, mounted above the stove, the average concentration in the test kitchen was 1700 micrograms per meter cubed. You can see the firepower is a little bit higher in this case, which will increase the concentration. If we had kept the firepower the same, we'd expect the concentration to go down. Then we had the larger fan mounted above the stove, and the reduction was down to 391 micrograms per meter cubed. And again, this is conservative because the firepower is even higher. Now we have that same fan with a hood. We went down to 149 micrograms. You can see the percent change from the baseline here, where there's no direct source ventilation. We just have the ventilation simulating what you would find naturally in the room, 15 air exchange rates. And finally, we have this natural draft hood. One thing to note about this was that we turned off the fans because the hood would not draft when the fans were going. The other thing that's different is we had to cut the hole in the wall so that the hood would draft. Finally, we were inside the test kitchen when we did these experiments because the concentration was so low. This was low enough, this 88 micrograms per meter cubed, that was what the average was over the 30-minute period. That was low enough that it wasn't a bother at all for the testers and for the neighbors that we came to show what was going on. It's a little bit conservative compared to the uniform case because the firepower is a little bit higher. Here's the same interventions, but we have different units. We have the 24-hour average kitchen concentration in micrograms per meter cubed. The way that's achieved, the way this number is achieved, is by dividing what we measured by 6. It works out because if you assume people cook for 4 hours a day, then the average that they'll experience over 24 hours with no other sources will be the number that we measured before divided by 6. The best thing, the most exciting thing here was that we got down to 15 micrograms per meter cubed with this natural draft hood. That's below the intermediate indoor air quality guideline from WHO, which is 35 micrograms per meter cubed, and it's very close to the ultimate guideline, which is 10. The last thing I want to take you through is the rollback model that I did using the Oak Ridge, Oregon, LRAPA data. And so we had the measured values, so they measured 40 micrograms per meter cubed in the inventory area, and they had total emissions of 552 pounds per day of PM. That came from the road and from heating stoves and some industrial sources, but most of the emissions came from the heating stoves. So the first thing I did here is just show that if all of the heating stoves met the 2020 standard, the outdoor air quality would be 13 micrograms per meter cubed. This is using their methods. It's very straightforward. And I estimated that the stoves that exist, each one of them is 153 milligrams per minute, but the 2020 is 36 milligrams per minute. What I've done here is if people in that valley were cooking with a 3-stone fire at 66 milligrams per minute, and if they were using the hood, then their indoor air quality would be 45 micrograms per meter cubed. That's outdoor plus indoor. Then here's the one, this is using our test kitchen rocket. It was a dirty rocket stove at 34 milligrams per minute. Outdoor air quality is 15, so then add 15 on top of that. That's exactly what we measured in the test kitchen. So indoor air quality is 30 micrograms. That's using a basic rocket stove with a basic hood with stoves that are on the market for heating. And now you've seen the context. We had low emissions inside the kitchen, and for that particular valley, and there's other models that can be done, we have not enough pollution outside to create a health hazard.
We had the fan on high, pointed through this exterior door. That's what allowed the air to circulate and ventilate out of the outer structure.